So we are, for simplicity, we're going to work with the same definite integral that we worked with for the first example, the integral from 1 to 2 of e to the 1 over x power dx. But this time, I want to find out how many subintervals would guarantee that the midpoint rule approximation for this integral would be accurate to within 1/10,000th. Okay, so now what we're doing is we are, rather than just saying, hey, let's use this many subintervals, we're demanding a certain level of accuracy, and we want to know how many subintervals we would need to get that level of accuracy. Okay, because I don't want to waste time. I don't want to waste. I mean, if I need a certain level of accuracy, I want to use the right number of subintervals. Okay, let me give you a moment to copy this, and then we'll continue. So if we wanted to find this value of n, okay, if we wanted to find this value of n, let me ask you, can you tell me if the value of n, the number of subintervals we would need to use, would it be greater than 10 or less than 10? That's right. Why would it be greater than 10, Ange? Why would that be?
Because the more division we have, the closer we get, the smaller is the area that we lost or gained.
Okay, all right, okay.
Like on the curve, whether it's concave up or concave down, if the interval, the area under the curve is smaller.
Well, and let's remember too that when we used 10 subintervals, in other words, when n was equal to 10, the bound on our error was equal to 0.0003398, right? How does 0.0003398 compare to 0.0001? Is it larger or smaller? So if you compare this decimal, 0.003398, that's larger. That's right, Ange. That's larger than 0.0001. So using 10 subintervals it may be enough, but I don't know. All I can say is when I use 10 subintervals, the bound on the error, the bound on the error using the midpoint approximation for 10 subintervals is less than or equal to about 3/10,000ths. I don't know if the error is less than 1/10,000th, it's less than 3/10,000ths, and maybe it's less than 1/10,000th, but I don't know. I need to have this error bound here be equal to 0.0001, right? That's what I want. So let's go ahead to the solution and work this out. So we require that are error bound, and we already know that 3 times z is k. We found that, let me say this the right way. We found that from the previous example, so we don't need to redo that again. K is 3e, b is 2, a is 1. The question is, what's n going to be? What's n going to be? So now where I have n, I don't have an n in there. I'm trying to look for n. But I know that this error bound, I want it to be less than or equal to 1/10,000. Okay, so the error in my approximation would definitely be less than 1/10,000 if I could find a value of n such that the error in my approximation is less than the error bound. So this whole error bound here, this whole error bound is equal to 3e over 24n squared. That's going to be less than or equal to 1/10,000. And now I have an inequality that I can solve for n. So what we can do is we can multiply both sides of the inequality by 24n squared. Hold on, I don't want to get sloppy. Okay. Now, oh wow, the inequalities didn't change. You know, when we multiply through inequalities by numbers, sometimes the inequality switches, right? Like from less than or equal to greater than or equal. But that didn't happen here. Why is that the case? Why is that the case when we multiply through the inequality by 24n squared? The inequality stayed less than or equal to. Why would that be? For any value of n, any number of subintervals, what would 24n squared always be? It would always be positive. That's right, Taj. So very good. So this is true. And now n squared, if I divide both sides of this inequality by 0.001 times 24, that's positive as well. That doesn't change the inequality. It's really beautiful mathematics here. We end up getting n squared is greater than or equal to 3e over 0.001 times 24. Now we have to solve for n. We haven't solved for n yet. Okay, so naturally, take the square root of both sides of the inequality. So see, we can take the square root of the left side and the square root of the right side. Well, the square root of n squared is n. N is greater than or equal to the square root of 3e divided by the denominator 24 times 0.0001. That means n is greater than or equal to 58.29. Are there any questions on that? Well, how many subintervals are going to be needed? Can I have 58.29 subintervals? Is that possible? That's right. That's right, Touch. You can't have a fraction of a subinterval. So either you know, let's see here. Well, if I round 58.29, I get n equals 58. But would 58 be the number of subintervals? Would that be right? Or would n equals 59 be the correct number of subintervals? What do you think? What's the right choice? 59, that's right. Very good, Ange, very good. Because you see, you can't do 58 because you need at least algebraically 58.29. So therefore, the number of subintervals would have to be 59. Even if n were, let's say n were greater than or equal to 58.001, n would then be 59. So you have to round up basically. You have to just I mean, I think you understand. So therefore we would need 59 intervals to achieve the accuracy that we want. We would need 59 intervals. All right, are there any questions on that? You notice that you need quite a few more intervals to get that. I mean, the accuracy is by a factor of 3. What I mean is basically with 10 subintervals, your accuracy is guaranteed to be within roughly 3 10,000ths. But if you want an accuracy to within 1 10,000th, you have to increase the number of intervals 6 times. So it's and again, this kind of information is helpful because if you're a computer scientist and one of your colleagues wants you to approximate an integral and wants a certain level of accuracy, well, you might find out you need to have a billion intervals or a trillion intervals, and even for, I mean, I'm of course the computer science folks here have probably more knowledge, but it takes time to compute things. When you have to compute a lot of things, it takes time, and you have memory issues and all that, right? It really is valuable to know how many subintervals you need to use, because then you can give the scientists the accuracy. They give them an estimate that is accurate enough for their work, right? Okay, I'll stop the recording here if there are no questions.